Okay, so today we're going to learn about titration curves for AP Chem. So these are the symbols. Most of the time they're going to give you these symbols and they're not going to really put B, but I just put those there just in case you see them and you don't think they're crazy. So you know it's going to be an acid if it has an H, because the definition of an acid is it's willing to give up a hydrogen / proton to the solution, which creates hydronium. And you know it's a base because it's willing to accept the hydrogen, and that's why there's a minus right here, because it's charged and it's going to accept the positive proton. The strong base is, of course, hydroxide, and the strong acid is, of course, hydronium. And you know that because in AP Chem we work with HCl and NaOH, and when you put those into water and make an aqueous solution, they really separate into hydroxide and sodium. So these are free floating, they're not attached to the sodium because it's a completely strong base. And for HCl, it would just make hydronium and chloride, and this would be separate, not attached to the Cl because of how high Ka is, that they would completely separate. Or mostly completely. There's going to be a few that didn't. Types of curves. So this one is in AP Chem, so you don't really have to worry about it. Strong acid, strong base. The important part here is that the equivalence point is exactly at 7 all the time when you use strong. So that's an easy multiple choice question. That's also important for qualitative analysis when they ask you in a free response. So it's just good to know that fact. You know it's going to start with an acid, and you're titrating an acid with a base, for say. When it's below the 7, this is the starting point. When it's below the 7, that means you're starting with an acid. When it is above this, when it is above the 7, you're going to start with a base. And so if it's close to the 7, like this is around 3 to 4 pH, then it is going to be considered a weak acid, as opposed to how it's all the way down here. That's going to be a strong acid. And this is a weak acid. And that goes the same for if it was a base. If it was right around here, it would be a weak base. And if it was right up here, it would be a strong base. And so when you use a strong substance to titrate with, which is most of the time, it's going to push the curve all the way up towards that. So when we use a strong base on the strong acid, then it's going to push it all the way up here. But when we use a weak base on the strong acid, it only keeps it around this level. And as you see, strong base pushed all the way back up here. Don't have to worry about this one. So what's in the curve? Right through here is your buffer zone, because the definition of a buffer is there's both the acid / base and its conjugate, and they're in the solution. They don't have to be equal, but in this situation, whenever you have in titration curves, the halfway point's definition is that the moles of the concentration of the acid equals the concentration of the conjugate base, and vice versa. And so that's going to be important because they might ask you a question, given the graph, what's pKa? And so you go to your halfway point, which you determine, you take your equivalence point, and let's say this was 30, and you half this volume, and you get it at 15, and you'd come all the way up here, and then you'd come to the side, and let's say that was pH of 3, then you'd say, you take the negative log of 3, and you'd say 1 times 10 to the negative 3 would be your pKa. And I'll explain how that works mathematically and why that's a thing in the next slide. Now, the definition of an equivalence point is the moles of the hydroxide is greater than the moles of the acid initially. And of course, the actual definition is the moles of the substance added equals the initial moles of the substance, because if this was an acid, that wouldn't necessarily make sense. So if this was a base, then it's the moles of hydronium equals the moles of the base. And what's important there is usually you're going to have an indicator here, which is going to be the last thing we talk about. And so you know when this happens. And so you're going to know both of these moles, and that's how you're going to determine, because the whole point of this is we want to determine the concentration of the original substance, and knowing that these moles equal each other and knowing the volume of the base added, we're able to determine the concentration of the original acid. Now, past here, of course, if you keep adding a bunch of strong base, after a while, the strong base is going to take over, and that's why it kind of evens out. And this is called the excess region, pretty much. They rarely ever ask questions about this, except they might show you a diagram saying on the molecular level what's present here, and you want to pick the one with the most hydroxide, basically. And there's not going to be a lot of other things besides hydroxide, but and if hydroxide was paired with like NaOH, then Na and OH are going to be the most present because Na doesn't go away during this if you're adding that. Moving on. So math-wise, what do you see in the titration curve? So the buffer zone, which you should know is the slant, you're going to want to use Henderson-Hasselbalch, which is this equation, and you get that on your green sheet in AP Chem, so don't worry about memorizing it. And of course, if this started with a base, you could either just change POH into, or use this and then change the PKB they would give you into PKA, and then use the same formula. Or you could use the other formula. I recommend learning this formula and only this formula and converting whatever they give you, because this is the formula they're going to give you on the green sheet and it's just easier to learn. So back to why when you have the halfway point and why you can figure out pKa. Well, at the halfway point, you should know that these two are equal. So if those two were equal, then if you divide something by itself, it always equals 1. So the log of 1 is 0. If you add 0 to anything, it's just going to be itself. 1 plus 0 is 1. 2 plus 0 is 2. So in other words, at halfway, this whole part of the equation doesn't even exist. So it's just pH equals pKa. So then it's just the negative log of whatever pH you have here equals your Ka. So if it's a pH of 3, then it's going to be 1 times 10 to the negative 3. Now, at the equivalence point, you're going to want to use a mole tally table to take the moles added from the base and the moles of the initial thing are going to be equal. And so to figure out the moles added, you're going to have the volume and they're going to give you the molarity of the base. So if the molarity of the base was 1 and you added 0.1 liters, then you would multiply those together to get the moles, and that moles would equal the moles of the original substance also. So you'd plug that into your mole tally table, and you'd end up getting 2 mole amounts that you would then divide by the total volume. So they're going to give you initial volume, the acid, and then you add that to the volume of the base you added, and this is the part that everybody messes up, so focus here. They're going to tell you in the original problem that there is an amount of volume of the original substance. They're going to say, let's say 1 liter of it, and you added, and then they're going to show you this curve and it's going to say you added 30 milliliters or something to it. You have to add both of those, and when you get these 2 moles at the end of your mole tally table, your molar amounts, you have to add those together, then divide to find the concentration. A lot of people are just going to want to divide by this number or this number. You have to add them together, then divide, and then you're going to get molarity, and with molarity you use the ICE table. With the ICE table, you're going to want to switch because this is an acid concentration, they're going to give you pKa, but as soon as you have to flip the mole tally table into an ICE table, you're always going to have to switch your pKa into pKb if you start with an acid, and with that you should be able to find the concentration of the original substance. Here I don't have listed the math you do for excess because they don't have you do the math for excess. And Lorson and Findle are going to glance over it, and it's not as important. I would really just focus on the conceptual what is here, which is there's a bunch of OH and whatever spectator ion was with the OH. So which indicator do you use? This every time you have a titration question on your test, they're going to ask you at the end, well, what indicators should you use? And people get a little freaked out. It's not as hard as it seems. The equivalence point, you just follow it to the pH, and then you just take the negative log of that pH, and it equals the pK of your indicator. So I know that sounded complicated, but basically you're going to follow the equivalence point. It's 6. So then pick the indicator with 1 times 10 to the negative 6. You're done. And you don't even need to memorize any of these indicators. They're going to give you a list with all their pKa's, and they're going to say, pick one of these and explain why it is the best indicator for this. So when you're actually doing the titration, why the indicator is important is because it changes colors at the equivalence point. So you know exactly when the moles of